Welcome to this walkthrough of LeetCode problem number 1900, the earliest and latest rounds where players compete. In this problem, we're tasked with simulating a knockout tournament to calculate the earliest and latest rounds where two specific players will face each other. This solution requires careful planning and management of simulation logic. Let's dive in. In this problem, we are dealing with a knockout tournament where players are paired up in the order of their numbering, and only the winner of each pair advances to the next round. If there is an odd number of players in a round, the last player automatically advances without a match. This process continues until a single champion remains. Now, given the total number of players n and two specific players, first player and second player, we are tasked with finding two specific pieces of information: the earliest round in which these two players will face each other and the latest round in which they could possibly meet during the tournament. The problem will require careful analysis of how the tournament progresses, based on the numbering and pairing rules. The output for this problem will be a list containing two numbers, the earliest round and the latest round. The earliest round represents the minimum round where first player and second player will meet during the tournament, while the latest round represents the maximum round where such a matchup could occur. For example, let's consider the case where n equals 11, first player is 2, and second player is 4. In the first round, players are paired in the order of their numbers: 1 versus 2, 3 versus 4, 5 versus 6, 7 versus 8, 9 versus 10, and player 11 advances automatically without a match. The winners from this round include players 2, 4, 6, 8, 10, and 11. In the second round, the winners from the previous round are paired again, resulting in matches like 2 versus 4, 6 versus 8, and 10 versus 11. Here, first player and second player meet for the first time, which makes this the third round of the tournament. Therefore, the earliest round where they compete is 3. For the latest round, we consider how the tournament could progress to delay their matchup as much as possible. By carefully analyzing the structure, we find that they could meet as late as the fourth round. This gives us an output of 3, 4. Now, let's look at another example where n equals 5, first player is 1, and second player is 5. In the first round, players are matched as 1 versus 2, and 3 versus 4, with player 5 advancing automatically. The winners from this round are players 1, 3, and 5. In the second round, the remaining players are paired as 1 versus 5, meaning the two players of interest meet in this round. Since this is both the earliest and the latest round in which they could meet, the output for this case is 2, 2. Similarly, for the case with n equal to 8, first player is 4, and second player is 7, the pairing process shows that the earliest round they meet is the second, and the latest is the third, resulting in an output of 2, 3. The problem comes with several constraints and edge cases to consider. First, the number of players n can be as large as 10,000, which means our solution needs to handle large inputs efficiently. Both first player and second player must fall within the range of the total players, and they must be distinct. Edge cases include scenarios where n is very small, such as 2, where the two players might meet in the first round. If n is odd, one player automatically advances, which could delay certain matchups. Additionally, if first player and second player are consecutive numbers, they might meet earlier than in other configurations. These considerations will guide the design of an efficient solution to the problem. To solve problem number 1900, our goal is to simulate a knockout tournament and determine the earliest and latest rounds where the specified players, first player and second player, compete against each other. The challenge lies in the branching nature of the competition, where each round can evolve differently based on which players advance. One approach we can consider is a brute force method that involves exhaustive simulation. Here, the intuition is straightforward: simulate every possible sequence of matches in the tournament and identify where the two players face off. This method guarantees correctness because it explores all possible outcomes. To implement this, we would generate all potential player pairings recursively for each round, simulating both win and lose outcomes for every match. However, this approach has a significant downside: its computational complexity. With each match having two outcomes, the total number of states grows exponentially, reaching 2n1 in the worst case. While it ensures accuracy, it becomes computationally impractical for larger tournaments, especially when n exceeds 10. This limitation makes brute force unsuitable for the problem constraints, which allow up to 30 players. To address the inefficiencies of brute force, we can consider an optimized approach using backtracking with pruning. This method is designed to reduce unnecessary computations by leveraging several key insights. First, once first player and second player meet in a round, further simulation is unnecessary, so we can stop and record the result. Second, symmetry in the tournament allows us to skip redundant configurations. For instance, the outcomes of players 1 versus 2 are equivalent to 2 versus 1. Additionally, we can dynamically track the current round, avoiding redundant recalculations. In terms of implementation, backtracking is used to simulate valid match outcomes recursively. At each round, both win and lose scenarios are explored for each match. When the two players meet, the result is recorded, and further exploration is terminated early. This approach reduces the state space significantly, making it feasible for larger values of n, such as 30. While the exact complexity depends on the number of valid configurations, pruning ensures that far fewer states are explored compared to brute force. This method is efficient and guarantees correctness, though it requires careful handling of configurations to avoid errors. Another potential solution involves using a dynamic programming approach that relies on state compression. The intuition here is to represent the tournament state as a set of players advancing to the next round, transitioning between states based on possible match outcomes. To implement this, we can encode the active players as a bit mask, where each bit represents whether a player is still in the tournament. A DP table, DP, state, round, is used to track the earliest and latest rounds where the two players meet for each state. Transitions between states are based on valid match outcomes, allowing us to systematically explore all possibilities. This approach avoids redundant computations by iterating over valid states and transitions efficiently. While the state space is determined by the number of subsets of players, which is 2 to the power of n, the transitions between states are computationally manageable. However, this method comes with trade-offs. While it systematically avoids redundant calculations, it has higher memory requirements due to the DP table, making it less practical for larger values of n compared to backtracking with pruning. The chosen strategy for solving this problem is the optimized approach using backtracking with pruning. This technique strikes a balance between efficiency and correctness by reducing the state space while avoiding the complexity and memory overhead of a full DP solution. It is well suited for handling the problem constraints, particularly when n can go up to 30. The brute force approach, while correct, is computationally infeasible for larger inputs due to its exponential growth in states. On the other hand, the dynamic programming approach, though systematic, introduces significant memory overhead due to the size of the DP table required. Backtracking with pruning offers the best of both worlds. By leveraging symmetry and stopping early when the two players meet, it efficiently narrows down the search space. This ensures that the solution is both correct and scalable, making it the ideal approach for determining the earliest and latest rounds where first player and second player compete. To solve this problem, we simulate a knockout tournament where players are paired up in order of their numbers and the winner of each pair advances to the next round. The goal is to determine the earliest and latest rounds where two specific players, first player and second player, compete against each other. A key insight is that the players can only meet in the same round if they are in the same subbracket of the tournament tree. This happens when their pairing aligns with the pattern, 1 versus n, 2 versus n1, and so on. The earliest round occurs when they meet as soon as possible, typically in the smallest subbracket where they belong. On the other hand, the latest round happens when they avoid elimination and meet in the final stages of the tournament. This structure significantly reduces the problem size after each round, making it more efficient to simulate step by step. The approach begins by simulating the tournament recursively. First, we initialize the list of players, which contains all players from 1 to n, and set the round counter to 1. In each round, players are paired up where the leftmost player is matched with the rightmost player, the second from the left with the second from the right, and so on. Once paired, we check if first player and second player are in the same pair. If they are, we record the current round as both the earliest and latest round, depending on the context. If not, we determine the winners of each pair, advance them to the next round, and continue the process. Special cases, such as when first player and second player are in the very first pair in round 1, are handled explicitly to ensure accuracy. This step-by-step simulation guarantees that we correctly track when the two players meet. After simulating the tournament, the algorithm returns the earliest and latest rounds where first player and second player compete. The process leverages key insights into how the tournament structure works. Each round has the number of players, making the algorithm logarithmic in complexity. The pairing logic ensures that all possible matches are considered, as players are paired in a mathematically consistent order. By simulating each round, the algorithm can precisely determine when the two players meet within the tournament's hierarchy. The distinction between the earliest and latest rounds is based on how soon or how late these players are forced into the same subbracket, highlighting the flexibility of this recursive approach. The algorithm uses simple but effective data structures to manage the tournament. A list called players stores the current participants in the tournament. This list is updated after each round to only include the winners, progressively shrinking in size. For example, with n equals 8, the list starts as 1, 2, 3, 4, 5, 6, 7, 8, and reduces to 1, 3, 5, 7 after the first round, then 1, 5 in the next, and so on. A basic integer round is used to track the current round number. Key operations include pairing players, which is done by matching the ith player from the left with the ith player from the right, ensuring all pairings are covered. Checking whether first player and second player are in the same pair is a straightforward comparison. Updating the players list after each round ensures that only winners advance, reducing the problem size efficiently. The algorithm is efficient in both time and space complexity. For time complexity, pairing and checking matches require O(n) operations per round, and since the number of rounds is logarithmic, the total complexity is O(n) log n. This is because the number of players is halved in each round, significantly reducing the workload as the tournament progresses. For space complexity, the main requirement is the players list, which initially holds n players and shrinks over time. This results in a total space complexity of O(n). These efficiency characteristics make the algorithm well-suited for handling large input sizes, ensuring both accuracy and scalability. Here, we define a class called solution and implement a function named earliest and latest. This function takes three parameters, the total number of players, and the indices of the two players we are tracking, called first player and second player. Inside the function, there's a helper method defined as DFS, which stands for depth first search. It accepts a list of players and the current round number as inputs. The first condition checks if the two specific players meet in the current round. If they do, we calculate their positions in the list, I and j, and confirm that they are direct opponents by ensuring the sum of their indices equals the last index of the player list. If this condition is met, the function immediately returns the current round as both the earliest and latest round where these players meet. If the two players don't meet in the current round, we simulate all possible pairings for the winners of this round. Using a loop, we pair up players from the start and end of the list, moving inward, and add the sorted pairs to a set called next_round to avoid duplicates. When there is an odd number of players, the middle player automatically advances to the next round. This ensures we cover all possible outcomes. Now, to explore these outcomes, we initialize two variables, earliest and latest, to store the smallest and largest round numbers, respectively. For each outcome and next_round, we prepare a new list of players for the next DFS call by taking the first player from each pair. This recursive approach ensures we explore every possible path forward. For each recursive call to the DFS function, we compute the earliest and latest rounds by taking the minimum and maximum values across all outcomes. The earliest variable is updated by comparing the current value with the result from the recursive call, and similarly, the latest variable is updated to track the maximum round number. Once all outcomes are processed, we return these two values. Finally, to kick off the recursive process, we initialize the list of players as a range from 1 to n, representing all players in their initial order. The DFS function is called with this list and a starting round number of 1. The result of the DFS call, which is a tuple containing the earliest and latest rounds, is returned as the final output of the function. This approach ensures that we systematically explore every possible sequence of matches to determine the required rounds efficiently. Here, we start by defining a solution class with the main method earliest and latest. This method takes three inputs: the total number of players, the indices of the first and second players, and returns an array containing the earliest and latest rounds in which those two players might compete. To achieve this, we call a helper method DFS, passing in a list of players created by the createPlayersList method, the indices of the two players, and the current round number, which begins at 1. The createPlayersList method generates a list of integers representing all the players, numbered from 1 to n, which will be used to simulate the rounds. The DFS method is a recursive function that explores possible matchups. If the first and second players meet in the current round, it immediately returns the current round as both the earliest and latest in which they compete. Otherwise, it proceeds to generate all possible outcomes for the next round, initializing a set to store these configurations. The GenerateNextRounds method is invoked to construct all potential matchups for the next round. Once we have these next round configurations, we initialize variables earliest and latest to keep track of the minimum and maximum rounds where the two players might face each other. We then iterate over each possible outcome of the next round, calling the DFS method recursively for each configuration. This allows us to explore deeper into the round tree and compute the earliest and latest rounds for each possible scenario. At the end of this recursive exploration, we return the smallest value of earliest and the largest value of latest. This ensures that all paths have been considered, and we have the correct range of rounds. The GenerateNextRounds method uses a helper approach to recursively build valid combinations for the next round, ensuring that players are paired correctly based on the current matchup index. The GenerateNextRounds method manages the pairing process. If the current pairing has reached the midpoint of the list, the combination is finalized and added to the set of possible next rounds. Otherwise, we consider two options for each matchup: advancing the player at the current index or advancing their opponent from the opposite end of the list. By recursively exploring both choices, we ensure that all valid configurations for the next round are generated. After adding a player, we proceed with the recursion, and once that path is complete, we backtrack by removing the player to try the alternative option. This backtracking ensures that we exhaustively explore all possible pairings without missing any combinations. The flexibility of this method allows us to simulate each round's outcomes and ultimately determine when the two specified players might compete. In this example, we have 4 players, numbered 1 to 4, and we're tasked with determining the earliest and latest rounds where players 1 and 4 compete. Starting with round 1, the players are paired as 1 versus 4 and 2 versus 3. Notice that the first player, 1, and the second player, 4, are in opposing positions, meaning the sum of their indices equals the total number of players minus 1. Since they meet immediately in this round, the earliest and latest rounds are both 1. The final output is earliest equals 1 and latest equals 1. Now, in this example, there are 6 players, numbered 1 through 6. In the initial setup for round 1, the players are paired as 1 versus 6, 2 versus 5, and 3 versus 4. Again, we see that players 1 and 6 are in opposing positions because the sum of their indices equals the total number of players minus 1. This means that they compete directly in the first round. As a result, the earliest round where they meet is 1, and since they meet right away, the latest round is also 1. The final output here is earliest equals 1 and latest equals 1. For the final example, we have 8 players, numbered 1 to 8. In round 1, the players are paired as 1 versus 8, 2 versus 7, 3 versus 6, and 4 versus 5. Here, players 1 and 8 are directly competing because they occupy opposing positions. Their indices add up to the total number of players minus 1. Since they meet immediately in this round, the earliest and latest rounds are both 1. Therefore, the final output for this example is earliest equals 1 and latest equals 1. The time complexity of our solution is driven by the depth of the recursive DFS function and the number of pairings generated at each step. To understand this, let's break it down. First, consider the number of players in each round. With each round, the number of players is halved, meaning the sequence of players reduces as n, n/2, n/4, and so on, until there's only one player left. This gives us a recursion tree with a height proportional to log n, as the number of rounds corresponds to the number of halving steps. Now, at every round, we generate all possible pairings of players. If there are k players in a round, there are k/2 pairs, and the number of ways to pair these players grows combinatorially. This growth can be approximated using the Catalan number for k/2 pairs, which grows exponentially with a complexity of about O for caret k/2. Finally, the DFS explores all possible outcomes for each pairing recursively, leading to exponential branching at each level. This is the primary driver of the computational cost. When we combine these factors, the overall time complexity of the solution can be approximated as O for caret n/2. This exponential growth arises due to the rapid combinatorial explosion of pairings and the recursive exploration of all outcomes. Turning to space complexity, there are two main contributors. First, the recursive call stack requires space proportional to the recursion depth, which, as we calculated earlier, is log n in the worst case. Each recursive call uses memory to store local variables and parameters. Second, at each round, we store all valid pairings in a set. The memory required for this storage depends on the number of players in that round. For k players, the number of pairings is approximately O for caret k/2, meaning the space usage is exponential during the initial rounds when the player count is highest. Overall, the space complexity is dominated by this storage requirement, leading to a worst-case complexity of O for caret n/2. Now, let's compare this DFS approach to a brute force or naive solution. A naive method would simulate all possible tournament outcomes exhaustively, which results in factorial time complexity, O, n1, as it would consider every possible permutation of players. The DFS method, on the other hand, optimizes this process by taking advantage of pair symmetry and pruning invalid outcomes. These optimizations reduce the complexity to an exponential O for caret n/2. To understand why the DFS complexity is exponential, consider the mathematical basis. The number of pairings in each round grows exponentially due to the combinatorial possibilities. Moreover, the recursive DFS explores all these combinations, resulting in exponential branching. While the recursion depth is logarithmic, the sheer number of possibilities at each level dominates, keeping the overall complexity exponential. Examining different scenarios, the time complexity can vary based on when the two target players meet. In the best-case scenario, if the first player and second player meet in the very first round, the DFS terminates immediately, resulting in O1 time complexity. On average, the time complexity is exponential, O for caret n/2, as most cases require exploring multiple pair combinations across several rounds. The worst case occurs when the two players meet in the final round after all possible outcomes have been explored, which also leads to exponential O for caret n/2 complexity. In conclusion, while the DFS approach significantly optimizes over brute force by leveraging symmetry and pruning, its growth remains exponential due to the rapid combinatorial explosion of pairings. This makes the method practical for small values of n but computationally infeasible for larger n. Here, we're discussing some common mistakes that arise when solving this problem. First, failing to correctly handle the base case is a frequent issue. Remember, the recursion needs to terminate when the first player and second player are scheduled to compete. If this condition isn't properly identified, it can lead to infinite recursion or incorrect results. Next, there's the mistake of not accounting for player index shifts. After each round, the indices of players in the next match change dynamically as players are eliminated. If you don't track these changes, the logic can break down. Finally, attempting a brute force simulation without pruning invalid states is inefficient. While it may seem simple to simulate all possible matchups, this approach becomes computationally expensive as the number of players grows, making optimization a necessity. Another critical mistake is overlooking symmetry in the problem. Symmetrical cases, such as players meeting in reverse order, are essentially identical and can be treated as the same state. By recognizing and leveraging this symmetry, you can significantly reduce the state space and improve efficiency. Additionally, it's essential to respect the constraints on player positions. The first player and second player must compete within their respective brackets. Ignoring these constraints can lead to invalid matchups and incorrect calculations. Properly managing these details ensures your solution is both correct and efficient. This problem is a great way for interviewers to evaluate your understanding of recursion, combinatorics, and optimization. A key insight here is balancing recursion depth while minimizing redundant calculations. To break down the problem, you should clearly explain the process of transitioning from one round to the next, how players are paired, and the condition under which recursion terminates. Optimization techniques such as memoization or pruning are essential to avoid recalculating states you've already explored. Be prepared to address edge cases, such as scenarios with only 2 players, very large numbers of players, or situations where the first player and second player are on opposite ends of the bracket. These insights demonstrate your ability to think critically about both correctness and performance. If you'd like to explore related problems, there are a few worth noting. LeetCode 46, Permutations, involves generating all possible permutations, which is conceptually similar to exploring all potential matchups in a tournament. LeetCode 77, Combinations, focuses on generating combinations of elements and can help deepen your understanding of pair elimination. LeetCode 1040, Moving Stones Until Consecutive 2, requires careful simulation of state transitions, paralleling the dynamic changes in player indices here. Finally, LeetCode 778, Swim in Rising Water, is an optimization problem that also deals with dynamic state transitions, providing useful insights for tackling this problem effectively. There are also alternative approaches to solving this problem. A recursive simulation with memoization is more efficient than brute force since it avoids redundant calculations by carefully tracking states. Its time complexity is O(n) per round due to memoization, which helps reduce the overall complexity. An iterative simulation is often easier to implement but can become less efficient for large values of n, as simulating every round iteratively may take O(n squared) in the worst case. Finally, using binary search to determine the earliest and latest rounds where players compete is another option. This approach is highly efficient when combined with symmetry reduction, achieving a complexity of O log n for searching rounds. However, it can be more challenging to implement due to the setup costs involved. Each of these methods has its trade-offs, so selecting the best one depends on the specific constraints and requirements of the problem. To wrap up, we explored how to solve LeetCode problem number 1900 by simulating a knockout tournament using recursion and backtracking. This problem highlighted the importance of simulation techniques and reinforced key concepts like managing multiple paths and exploring combinations. Thanks for joining, and don't forget to like and subscribe for more problem-solving tutorials. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!